Welcome to this Diversity Era course on pre-emergent herbicides. I'm Dr. Chris Preston from the University of Adelaide, and I'm going to be taking you through how pre-emergent herbicides work. This is Module 4, and in Module 4 I'm going to be looking at pre-emergent herbicide persistence, the factors that affect that persistence, and when too much persistence can be a problem. So the main topics I'm going to cover in this presentation are going to be about how herbicides break down in the environment, where they go. We're going to be looking at the different types of breakdown, so microbial breakdown and chemical breakdown. We're going to be looking at issues around too little breakdown, so causing plant backs to following crops. And then we'll finish off by talking about some examples of too rapid breakdown. To start off, we've got to be thinking about what actually happens to a herbicide when we put it out in the environment. And the answer is, well, actually lots of things can happen to it. So this is a diagram that shows all of the places that a herbicide can go when it goes out in the environment. So we spray the herbicide out, and the action we want is that we want it to be taken up by plants. But that's not necessarily where all the herbicide goes. We can have situations as on the left-hand side where we can get some runoff into rivers and lakes. That's something we don't want to have. We can have leaching of the herbicide, so if we get too much water, the herbicide can move out of the root zone and can get down into groundwater. It's not a lot of use down there. But the herbicide that actually stays in the soil zone and doesn't get taken up by the plants could be absorbed by soil components. We've already talked about that. It can volatilise if it's left on the surface and end up in the atmosphere. It can be broken down by sunlight, what we call photochemical degradation. It can be broken down chemically in the soil, so that's the chemical degradation, or it can be broken down by microbes. So for any herbicide we're putting out, all of these processes are happening to one extent or another, and they're all leading to loss of that herbicide from the soil. So part of our management of pre-emergent herbicides is to make sure we don't lose too much too soon and that we don't keep too much for too long. So when we're thinking about the factors that are important for herbicide degradation in the soil, the main ones are photodegradation, hydrolysis, and microbial degradation. Photodegradation is degradation by light. Hydrolysis is a chemical process, it requires water. And microbial degradation is breakdown by microbes. The key factors that affect all of these are soil moisture, soil temperature, and for microbial degradation in particular, soil organic carbon. So the reason that these factors are important is that if we don't have soil moisture, then we're not going to have the herbicide broken down by microbes because our microbes aren't going to be growing. We won't get hydrolysis because that requires water. And we also won't get a lot of photodegradation because the herbicide will actually be bound to soil components. And it's only really available for photodegradation when it's free from those components. For most of the herbicides that we've been talking about in our pre-emergent herbicide use, photodegradation plays a minor role in their breakdown. The main role is played by microbial degradation. So this is the big one. And one of the reasons why we know microbial degradation is important in the breakdown of herbicides is because we can track what happens if we take the microbes out of the equation. So this is some data looking at S-metolachlor breakdown in soil that's been sterilised, so all the microbes have been killed, or soil that's been unsterilised, so the microbes are still there. And so what we've got is the amount of herbicide that's left, so the percentage of applied that's still left, looking at incubation time in days. And if you sterilise soil, after 60 days, there's 65% of the herbicide you applied still there. But if you use unsterilised soil, you're looking at 20% of the herbicide that's left. So it's the microbes that are doing most of the breakdown there. So this is true of most of the herbicides we have to worry about. So this means that when we're thinking about herbicide persistence, we're going to worry about what our microbes are up to. We know that degradation is going to be higher in moist soils because we're going to have greater microbial growth. We know it's going to be higher at higher temperatures because we're going to have greater microbial growth, but they'll also be degrading the herbicide faster. And we know it's going to be higher in soils with higher organic matter because we have to have something to feed the microbes when we're not feeding them herbicides. So organic matter is what they normally live on. Those are the main factors that are going to be affecting the persistence of a lot of the herbicides. So here's some examples of how that all works. On your left, we've got degradation of S-metolachlor again, but here looking at a range of different temperatures that the soil is at, ranging from 10 degrees to 35 degrees. So 10 degrees is the closed circles on the top there. And what you can see is that as you increase the temperature, you increase the rate of degradation of S-metolachlor in this system. So at 10 degrees, after 60 days, there's about 55% left, and at 35 degrees, we're down under 20%. On the graph on the right, we have the influence of soil moisture. So this is looking at the amount of water in the soil compared to field capacity. So at 20% field capacity, degradation is slower than it is at 80% field capacity. So if our soil's dry, we're down in the 0 to 10% field capacity, we're not going to get very much degradation at all. Once the soil gets up over 20%, we're going to get degradation, and then it'll increase as our soil gets wetter, but it actually can get too far because if our soils get waterlogged, then our microbes aren't going to be degrading the herbicide at all. So temperature, really important. Soil moisture, really important. Organic matter is very important. Now, there are other processes that can contribute to degradation of herbicides in soils. And one of those is chemical degradation. In this case, I'm talking about hydrolysis. Hydrolysis is simply adding water across a bond in your herbicide. This example here is chlorsulfuron, which is the active ingredient in glean. And you add that water molecule, you break it into two parts, and it's no longer a herbicide. Now, mostly hydrolysis tends to be a minor component, but it can actually become a quite important component under certain circumstances. And chlorsulfuron is a good example of this because in acid soils, the amount of hydrolysis of chlorsulfuron increases dramatically and it becomes a substantial component of the breakdown. However, in alkaline soils, virtually no hydrolysis goes on and we're only relying on microbes to break it down. So one of the factors that increases persistence of chlorsulfuron in alkaline soils is the fact that there's no hydrolysis. This process, like microbial breakdown, requires moisture and temperature. We want to have the right amount of persistence of our herbicides. And one of the difficulties we get into with pre-emergent herbicides is that they can be too persistent. And that persistence can cause us problems in terms of the next crop we're going to plant. And the main things that we have to worry about there are the herbicides that we've been using and the tolerance that our crop has to those herbicides. The other major impact on this is the amount of rainfall since application. Temperature, as I mentioned before, matters, but rainfall matters more in our environment in Australia. Now, the next two slides have a series of herbicides for which there are plant packs on our labels to sensitive crops. These are something that should always be considered when using these herbicides, because if you don't get the right rainfall patterns and the herbicides don't get broken down, then you can have situations where the crops get damaged. And there is a wide range of herbicides for which we do have plant back or potential plant back issues. These are some of those herbicides. So in fact, all of our Group B herbicides, the sulfonylureas, the imidazolinones, the products like flumethylam and so on. We also have it with our Group C herbicides, with the triazines, the triazonones and the ureas. And we do have plant back even for our Group D herbicides. things like dinitroanilines such as pendimethalin and trifluralin. There are plant backs for our group H herbicides, particularly important for isoxaflutol, and even in herbicides that we actually don't consider to really have a lot of pre-emergent herbicide behaviour. Our group I herbicides have plant backs, products like dicamba, clopyrrolid, picloram, for example. You should consult the labels to determine both the amount of time and the amount of rainfall from application to planting a sensitive crop. And you have to worry about not just the amount of rainfall, but how that rainfall falls. A rule of thumb is that you need the surface layer of the soil moist for about a week to get any significant breakdown of herbicides. So light showers in the summertime generally don't do very much. And mostly what we find in southern regions is that a lot of the breakdown will happen in spring or in autumn. In northern regions where we have more summer rainfall and higher summer rainfall, most of the breakdown is going to happen following those large showers, those large thunderstorms. So whilst we worry a lot about herbicides persisting too long and causing us a problem, we can have the opposite issue, and that is where herbicides don't persist long enough. One of the nature of pre-emergent herbicides is that they have a range of persistences, and we need to factor this in terms of our management. And some of them tend to have fairly short persistence, which means they're not going to control weeds for very long. But then we can have a problem where the degradation in the soil has become too rapid and we get unexpectedly rapid degradation. This figure shows a data set from orchards in California, but the issue happens in Australia as well. And this is looking at simazine degradation. Now, normally we would think of simazine as being moderately persistent in the soil. So what this figure is showing is that how much degradation you get of simazine depends on how much simazine's been used in the past. So in this case, the green symbols there at the top have been no prior use of simazine. And what's seen there is that it's got quite a long persistence. So more than half the herbicide is still there 10 days after application, and quite a lot still there 30 days after application. Where there has been use of simazine in the past, then the herbicide gets broken down more quickly in the soil. So if there has been annual use, so that's the red symbols, the red line there, then the breakdown's really quite rapid. Even if there's only been annual use for a relatively short period, that's the orange symbols, the breakdown is still very rapid. If there's been a short break since recent use, then that will slow the breakdown down a little bit, but you still don't get back to where you were in a completely naive soil. So what happens in these soil types is that the herbicide is broken down by microbes who then use the components of the herbicide as nutrients, and particularly looking at things like nitrogen. What this does is favour microbes that are able to break down that herbicide. So if you use the same herbicide over and over again, you tend to build up a population of microbes that are able to use that herbicide for nutrients, and they grow at the expense of the microbes that can't. So you favour these degrading microbes. And you get to the point where their numbers are so large that they break the herbicide down almost instantly that's put out into the environment. And that's when we find we have situations where the herbicide doesn't work anymore. We've had these in Australia, particularly around herbicides such as propizamide and carbetamide used in the pasture seed industry, where they were used year in, year out for very long periods of time. So to sum up this module, the things that we need to be thinking about in terms of the persistence of herbicides is where that herbicide is going to go in the environment, and are microbes going to be able to be present and break it down. Microbes require moisture and temperature to break down herbicides, So most of the breakdown is going to be done under warm, moist conditions, and less breakdown is going to occur under hot, dry conditions or under cold, wet conditions, or even cold, dry conditions. We need to worry about the persistence of herbicides and make sure that there has been both enough time and enough rainfall, and that rainfall has occurred at the right time to break the herbicides down. And very occasionally, we could run into problems where the herbicides break down too fast. In the next module, I'm going to be looking at incorporation of pre-emergent herbicides and stubble management, and when do we need to do it and how much do we need to do it.